Moving into graphs is both significantly easier than some other data structures, but then it also scales up to be amazingly, interestingly complex. We're just really going to cover some of the easiest stuff here, especially in these first couple videos. So really graphs are a way of representing relationships amongst data. I mean, you can see this picture here is very typical of the type of thing that's going on with a graph because there's all sorts of ridiculous numbers of relationships here, and they are always contextualized and mean something. Graphs rarely are a standardized data structure like some of the others we're talking about and some of the other ones that we're used to, such as the different relationships amongst data structures that we had in lists, sets, or maps, or symbol tables, if you want to call them as such dictionaries. So lists have this notion of just simply when was it entered into the list. Did it come first? Did it come middle? Did it come last? You can kind of insert things, but the main relationship is I come before or after some value, normally in some sort of temporal insertion order or some other meaningful order given by the program or the application. Occasionally, we can talk about queues and stacks within lists, which slightly changes that order, but again, it's mostly about insertion order. Sets don't really have any particular relationships outside the fact that they're a set. There's a limited number of things. They're all kind of grouped, but there's only one of each of them. And then maps are similar because there's no particular relationships outside they're contained in the maps, but there's a relationship between the key and the value. And so you have this set of keys, and then it relates to a value. So all of those are wonderfully nicely constricted relationships in general. So creating standardized data structures that represent them and store them is fairly reasonable. You can go off and create a generic set map or list and do something functional. You can create kind of sort of generic graphs, and we'll see some basic implementation of that. But for the most part, when we're talking about data with relationships, it represents all sorts of diverse things. So if we talk about a map, interestingly enough, can be considered very much a graph relationship. Now, how you do that, I'm sure there's a lot of different variations inside of it. I'm not an expert on geographic information systems by any means, but you could view it as each intersection here between the streets, and this is a map of Chicago if you don't recognize it right away, but each of the intersection of the streets could be a different point, and then the flows between that. We'll learn more about the notion of edges and vertices as it goes, but that could be data represented inside of here. It could be different points, different buildings, different, any number of things could be represented as a graph, and there could be distances between them. There could be other relationships. This is there's maybe seen many of these. This is a flow chart of the different characters from the Lord of the Rings series and whether they interact or not. And there's actual physical people and there's races and whatnot. And you can see how some of them rise and fall and they grow and they intersect and whatnot. And that could be some sort of, different relationships inside of there. This is a time relationship, but could also have some sort of interaction relationship. And then, you talk about the different courses you might take here through class, through school. There's a relationship between there too. You'd have an introduction to programming, then you go into, perhaps data structures or computer systems, and then they lead into maybe perhaps an operating systems class or whatever. The CS1, 2, 3, 4. CS1 and 2 have a meaning in computer science research, education research, but the rest of them are just whatever number that it's 301 or 502 or whatever classes you might be taking. But there is some hierarchy. There's some relationship between these classes. So the most basic type of graph doesn't care about such hierarchies or relationships. They're just merely relationships or merely related. And so here, diving into the the Tolkienian world of Lord of the Rings and The Hobbit, there's characters here, and these characters have relationships. And so you might have, I mean, if you've watched the movies or read the books, you might be familiar with some of these relationships. And so these characters have some sort of direct connection to each other, and other characters may or may not have ever met. Oh, I'm actually missing a relationship here. Clearly, these two have met before. I don't know if, this is Aragorn. I don't know if you ever met over here with Thorin Oakenshield. I'm pretty sure Aragorn really never ran into Smaug. That would be a story worth telling. But he did, work with Gollum, with Smeagol for a time, in some of the early stories. So again, we don't know about time. We just know that these characters are connected, and we can find out the network of characters who knew each other in some sort of that social network type relationship right there. A friend of a friend. So that other type we just saw, sometimes we have directed graphs. And this directed graph talks about prerequisites. So before I can get into CS2 or computer systems here, I typically have to demonstrate the knowledge or take the class CS1, for instance. And so which direction the relationship goes and what that meaning is and how I model it is rather dynamic, but the idea is this notion that there is some meaningful direction to the relationship. Most streets are two-way streets, but sometimes you have a one-way street that would have a graph that has both two-way and one-way relationships inside of it. There's going to be different meanings and different ways of storing the data based off of that. So what do we use graphs for? Well, graphs are fundamentally a model of some data from the real world. And often we just simply use graphs as a way of creating visualizations. The first chart up in the top left here, I think if I remember right, it's some sort of mapping of the characters used in tweets, 140 characters, and what are the different characters used that show up in tweets and the relationships between them or something like that. So this is just a whole bunch of diverse data, and it shows how some data connects to other data, and you can see the visualization helps us see that with the colors and the size of the arcs and whatnot. Um, you know, Sometimes we use it for querying data. So again, social networks. Um, LinkedIn is very famous for trying to connect you to other people you might know or friends of friends or something like that. Definitely some way of querying it out there. And then you also have this notion of optimization. If you're going to go get driving directions off of a map, I want to have the shortest or the fastest or the safest or the not driving through neighborhoods sort of path. And maybe I'm going to a number of points. I want the optimal path necessarily that I'm not going back and forth, the least distance or the least time or the something along those lines. All these are things that computers attempt, and some of them become very, very, very hard problems. There's this notion of the traveling salesperson problem that becomes a very, very complicated problem to solve in a hurry in conventional computing approaches. So we have to think of very clever ways to attack these problems. So as we go through this next couple sections and these videos and the exercises, we're going to start here with a little bit of graph, quote unquote, theory. Graph theory comes from mathematics, and a lot of the terminology that comes in the books that talk about graphs will come from that mathematical terminology. I'm taking a very pragmatic view on this, and I renamed some things as I talk about it in order to move away from the simple variables of math into some more of the meaningfulness of of how you're going to build algorithms, how you're going to manipulate that. If you really study this stuff a lot, then those single letter shorthands for this will mean something, but you'll see me use some longer terms that hopefully mean the same thing, or at least close enough to the same thing to help you get this model of graphs in your mind. So just consider that. So we're going to talk about the representations of graphs then, how we put the data together inside of a high-level programming language. And then we'll talk about the algorithms for searching graphs at some point, and then all the different variations that can show up for specific data types as we go off and store data in graphs, and how we might, how we might bridge between existing data that we have and the type of representations we need for graphs. So that's a start. A little bit of some intro. We'll continue to dive into this in layers, and there'll be some fun exercises to work through on graphs as well.